Good afternoon. Good. Yeah, I'm also very thankful for being at this workshop. I think it's been an interesting collection of people that we would otherwise not, know about, or information we wouldn't learn from. There's even someone from Rutgers here who I just met. So it really, it's been great, so far. So I'm part of the Wind Lab at Rutgers, and I have a small lab now that I'm getting started. I've been at Rutgers for a year. Before that, I was at IBM Research, working on IoT, machine learning related things, and I run the Cyber Physical Intelligence Lab. So one of the two main applications that we sort of focus on for doing machine learning is smart buildings and health applications. So I don't need to sort of have a slide that motivates this, but from an engineering perspective, of course, we see that buildings are a prime target for doing a lot of this very interesting work of figuring out, where the energy is going, how to make them more efficient, how to use them more intelligently. And if we look at a typical building's energy consumption, here's a building actually on the UC Berkeley campus where I started some of this work. We can see that the power draw varies throughout the day. It's diurnal. If you look a little bit closer, you see that actually 2/3 of the energy is actually spent in the idle phase when there's no one there. There's not much activity. There's an active phase which takes up the last third. And there's this question of, well, what's happening? Why is it being activated? What are the activities that are taking place within it? And if you look at various studies, they show that a lot of that is wasted. There are studies throughout various sorts of one-off studies in typical buildings where it's clear that things are being activated and left on that shouldn't be, and this is affecting the energy envelope of the building. So traditionally as a computer scientist, we step back and we look at how, what's the most similar thing in computer science. It sort of looks like this, and we can think about the way that servers consume energy. Here's a graph of the CPU utilization relative to the amount of time that it's within, using that amount of CPU power. And what we're really seeing in this chart here is that the amount of power consumed even at low utilization is quite high, very much like the building context, and that the efficiency is very low at low utilizations. And what we'd really like to move towards is having very quickly ramp up our energy efficiency for the typical usage range of the operating region of the server, and for the power to scale linearly with the work that the CPU is doing. So how do we then, broadly speaking, cast this same objective to the building context, given that 2/3 of the energy is consumed in idle and 50% of it is wasted? Where is it all going? Okay, so that's where the IoT and machine learning aspect of the problem comes in. We say, great, well, we have, the first goal is we want to reduce that baseline. And so essentially we need to figure out how to do nothing well, right? If you're not using it, it should be off. If it shouldn't be active, it shouldn't be on. And we need a way of improving efficiency. So from the building perspective, how do we support the work that's going on in it? And so this fundamental question of, well, why are things being activated? Well, that means we have to basically measure everything and see what we learn. What processes can we actually load shift? What things can we actually activate or deactivate? And that's where the IoT angle comes into play as well. And so there's a question of both, is the sensing that's there enough? How can we add more sensing? And what kind of analysis can we do to disaggregate a lot of what's going on? Ultimately, the buildings we've been looking at, they all support human activities. Humans drive and regulate all of the activity in the building, including things that are happening on servers. And we see that in that interaction, the building knows nothing about the people, or very little. Lights are left on, their filters are dirty, the building doesn't even know about itself. right? So it's working harder to maintain some of those set points and that airflow, and it doesn't know that it's wasting energy. And sometimes contractors come in and actually make the building even dumber than it already is. And we see that in various studies that actually human activities, by being able, if we go the other way around, it's not just the building, but also can we get the people to behave nicely. If we look very closely at this graph here, which is various interventions and their effect on the energy footprint, which is kind of hard to see here, just to pick out a few of these features, we see that if we change the set points, we can get roughly a 0.25% reduction in energy consumption. If we turn lights on or off, it can have a big impact on the energy envelope as well, up to 17%. And a 5% difference in the effects of the ventilation system, right? So clearly, it's not just one way. It's not just the building being smart, but also getting people, maybe even looking at people as a control knob as well, as a sort of probabilistic control knob. And so in our lab, what we've been examining is this sort of two-pronged approach of how it is that we incorporate people into this equation. And one is through explicit human feedback. We make a decision and we ask people how we're doing. And the other one is through implicit feedback, where we're simply observing, occasionally changing a few things, and then observing again. Okay? So that's essentially where broadly speaking, where the work falls into. So one thing we initially started looking at are anomalies just based on the data and seeing how far we get with presenting anomalies to a building manager. In this case, there are sort of indirect control knob at addressing some of these inefficiencies. And this is just a list of the most energy wasteful anomalies in buildings that was put out in a report a few years back. And so a lot of these can actually be detected just from the building management system itself. We designed an algorithm called SBS, or strip bind and search, where we essentially do some signal processing on the raw data that comes in. We re-aggregate it into particular bands of frequencies, and we use one of those bands to go from essentially a random signal in the raw signal space to something more meaningful after we've run the SBS algorithm. An interesting thing that we found post SBS is when you run correlations, you get this interesting spatial property where things that are very highly correlated post SBS analysis are sensors that are observing similar phenomena and phenomena in a similar space. So this is just showing how if you change the threshold on the correlation coefficient, the sort of scope of sensors that are included in the set increases. And so we leverage that in order to model canonical behavior and sensors that are activated in concert in order to support local building activity. And some of we actually ran this on several buildings. There was one building at the University of Tokyo a few years back where we found the AC being left on all night. Again, these algorithms know nothing about building systems. They're just doing this signal processing and doing correlation analysis. We found lights being left on all night. And we found simple changes in behavior that were anomalous only because we didn't incorporate weather data. So in this case, it may have just been a cooler day, which is why the AC wasn't left on, but it was still flagged, and this is presented to the building manager. We ran it in a very old building at UC Berkeley. Actually, this building has 15 different HVAC systems in it that don't talk to each other. And so we expected we would find lots of awful things happening. And of course we did. We found a chiller that was dysfunctional, a hackathon that happened on the weekend, which changed the energy consumption profile, and competing heating and cooling systems going on for 18 days actually. So when we alerted the building manager about this, it was quickly identified and addressed. So we actually took this and started running deployments across several campuses. We did 7 deployments in all, collected tens of thousands of data feeds, and we learned a few things. We learned that many of the statistical anomalies are actually not important. So while we were finding you know, 100 anomalies. This is a classic computer science problem of ranking things. What should we put at the top, right? Just because it's statistical and maybe it's even statistically significant, the building manager may not care that it's there. In order to be effective and actually induce changes in behavior, we better get buy-in from the building manager. In order to find, it's not just false positives, it's unimportant true positives that we need to identify. And so what we've been doing is really moving this into a different space where we're actually casting this as a reinforcement learning problem, where we're taking feedback directly in and adjusting our filters to account for what the building manager considers important. Okay, so I'm going to quickly, I only have 5 minutes, I'm going to go through some of the other work that we've been doing as well in the context of buildings. We deployed a set of sensors throughout a building space, just with these PIP sensors, these binary sensors of which doors are open and closed, and we use that in an IoT deployment to infer, you know, how people are moving throughout the building and how many people there are. And we actually ran this through a neural network which performed quite well at inferring the number of people with a simple $3 sensor. Okay. We've also been doing some human activity recognition. Everyone has a mobile phone these days. Boy, it would be great to, you know, to use that information to do smarter controls. We've actually taken IMU data from your phone, cast it in as an image using these things called recurrence plots, and then run it through a standard image classification pipeline that's been snipped together to actually fit on the phone and run in real time. So I won't go through all the details, but we were able to get it to run in real time on your phone. And so now if you opt in, we can actually tell what activity you're doing, how active you are, look at distributions of activity throughout the day, just from the phone that you're carrying in your pocket. So these are just some results that show that that worked quite well. I'm going to skip ahead to just one interesting thing that came up in our group discussion, and it's this notion of scale. And you know, there's a really important problem that I spent a few years working on, which is this notion that the building is actually an execution environment for these applications. But in fact, we have all these very different naming conventions underneath. And so while we'd like to run it once and run it everywhere, we're not quite there yet. And so we spent quite some time building up some tools to look at, say, take a sensor naming data point like this and get feedback from the building manager about how to decode these multi-character tags. And so by doing that, we can translate that into a normalized namespace and then write our applications on top of this normalized namespace. And if you look more closely, within just a single building, you get multiple schemas, you get a lot of inconsistencies, with the fundamental observation being that these were made to be, you know, understood by a human, not to be machine parsable. And so a lot of the machine learning that we did in this context was simply to do that translation and to have human feedback in doing that translation, because fundamentally it wasn't built for computers. And so, you know, we end up with this normalized namespace, and we actually we did some transfer learning and some active learning and combined them in order to show that the amount of work you have to do to suck in a new building into your system to write applications on top is actually less and less, because you learn all the various naming conventions as you go from building to building. And so this was another one where we also applied a program synthesis-based approach in order to learn the sets of rules to parse out these tag names. And we actually built a number of building applications on top. And I think this is one important thing that I actually threw in towards the end of today's talk, because, you know, while a lot of the studies that we've seen are these sort of one-off things that we run in a particular building at a particular point in time with a particular set of people, I think the real value comes in, you know, how does that generalize? I mean, I think we can make sort of interesting point observations without really seeing what the trend is. And we're simply not there from a systems perspective to be able to do that. I mean, that issue amongst others for being able to do this at scale. And so I think some of these sort of more computer science-y types of systems questions come up with how you would do that. Every building is unique. The set of people that are in them are unique. But even at the data level, they look quite unique. So you know, that's another set of challenges that we're also trying to address. And with that, I'll just put up some folks that I've been working with and links to some of the papers that we've had over the years.